So in the previous sessions, we have discussed about backpropagation and we saw the derivation, how do we derive backpropagation. So now in order to understand that backpropagation fully, what we should do, we'll take a small network and we'll do backpropagation by hand, okay? So what I can do is I can write over here backpropagation by hand, backprop by hand. So today's lecture is going to be very important because if you understand this, you understand the heart of deep learning. Okay, and as I said, deep learning is nothing but you are putting computation on probably on steroids. You do these computations very fast then, and otherwise you could have done it by hand. Okay, now we'll do that, how to do it by hand. For that, first we'll define a network. Okay, we'll define a tiny network. So in that tiny network, we will have two inputs and we'll have hidden layer 1, hidden layer 2, our different neurons. So what we can do is we'll have two inputs, call that x1 and x2. Suppose this is our input. And once we have these inputs, then what we can do is we can define hidden layers without giving the names first, because I might use different names first. So let's consider this as to be input, and then we have hidden layers. Consider this to be hidden layers, two hidden layers, and then we have an output. Let's suppose we have two outputs as well. So like, let's suppose this is our network. I'm making this network pretty symmetric. I could have done anything, and this is the fully connected network. So if you see, so this input will go here, and this input will go here, and now you have something of this sort. Okay, so this is your fully connected layer. So now we can name them as per the convention. We can do the same things and then call this. We have now h0, and you know by definition how we have given those symbols and stuff like that. You should probably knowing them by now. You should know them very better. So we have this h0. So h0 will be, we'll call that as an input. Suppose that input is x, and x we can define it as suppose 1 0. I'll take exact values that I have written over here so the calculation becomes easy. So we have its y, target, basically the thing that we want to get. So we have target 0 1. Suppose this is our target. Okay, so this is our input and this is our output. And now we know we have to initialize weights and biases. So how many matrices will be associated with this? So this is your input. Okay, and this is your hidden layer first, hidden layer second, and this is your output layer. So now if you see, we'll have matrices W1, W2, and W3. So we'll have matrices W1, W2, and W3. So these will be our three matrices. And now you know that each of these will be a 2 cross 2 matrix. Why? Because we have these 2 cross 2 neurons over here. We have 2 neurons in the input, 2 neurons in output. Similarly over here. So we'll have this W1, W2, and W3. So how to define that? I can give you some values over here. 0.1. Please have pen and paper with you. If you don't have, you can still grab the papers till I write down the problem, and then you will have to do calculations with me. So 0.3, and then this is 0.4. This is my W1, the weight matrix 1. This is associated in between layer 1 and layer 2. And then we have this W2. W2 over here that I have written is 0.5, 0.6, 0.7, and 0.8. And then we have this W3, it is 0.9, 1.0, 1.1, and 1.2. This is how it is defined. And now we also have to define bias vectors. So again, you have 3 W1, W2, W3. You have W matrices, matrices, and then you should have vectors. Bias 1, okay, bias 2, and bias 3. We'll give them pretty standard values so that you can also understand. So bias we can keep constant, 0.1, 0.1. Similarly over here, 0.1, 0.1 to make the calculations easy. This is 0.1 and 0.1. Okay, this is how our bias looks. And now you have k. Your k is equal to 1 is the hidden layer first. That is, if I write k is equal to 1, that means hidden layer first. When I write k is equal to 2, that means hidden layer second. Okay, and if I write, let's suppose k is equal to 3, that means hidden layer third output. If I write k is equal to 3, that is your third layer or output layer. So in this case, it won't be hidden, it will be the output layer. So all of these matrices, if you see WK, so what is this WK? They belong to R 2 cross 2. So they are 2 cross 2 matrices. And biases by BK and AK. AK will be our pre-activation. So basically when you have this, now when you apply this affine transformation or linear transformation. So all these things, and HK also. So if you see BK, HK, these all will be vectors. Okay, at each layer there will be vectors, and how they will belong to R2. Basically they will be a 2 cross 1 vector. So this is the problem setup. And now we'll have to numerically, so we'll do one pass of gradient. We will do one pass of backpropagation. For that, we first will have to do forward pass. You can help me in this. Can somebody help me in the forward pass? Give me a second. I will set up the tab accordingly. Now, once you understood this, the first thing that we have to do is our forward pass. We have to apply forward pass. The setup that I showed you was like this. We have to basically compute AK first. AK, this is affine transformation, and we have to compute HK. We can do it in two ways. In order to, for the understanding purposes, we can do it element wise. We can take, because as you know, this is the whole vector. This AK, this is a vector that you can know. This is a 2 cross 1 vector. This HK again is a 2 cross 1 vector. So what you should do now is you can do it. Suppose we'll do it element wise first. Let me just write that down. So what it has to be taken as linear sum. So if I have to compute, suppose ai of k, so you know that we have this matrix wk, and wk is 2 cross 2 matrix. So we'll take the wk, and in order to do that computation for a single point, for a single element, so what we should do is we'll fix the value of I. We'll fix one row. If this is the matrix and it is like something of this or 2 cross 2, so we'll fix this I. We'll fix one of the rows. If it is I1 or I2, it depends what we can fix. Okay, and then based on this, we can iterate over the columns. So we can iterate over the columns. That means we can write summation j goes from 1 to why, because only 2 columns, we have to iterate on only 2 columns. So wi and j. Okay, and this will give us one row, and this one row should be multiplied with hk. So how should we take that? Hk minus 1. Okay, and we have to only multiply with that with, let's suppose, jth entry. So if we have to have jth entry, because now this will be hk and you have to iterate over the jth entry. So hk will be something of this sort. This will be j1, this will be j2. Okay, this will be hk minus 1, the previous layer's hk minus 1. And then plus you'll have to also add bias. So bk is the whole vector. You just want a single point out of that. So based on these two things, this will be a dot product. So this you can perform over here. So this will give you one number. So this bk and then just j, or because here in this case it will be I, because we are computing the ith point. So ith point is, so this will be your affine transformation or the linear transformation, and you have to apply some sort of activation function on this. So here in this case we'll apply sigmoid function. So let's call this at h I of k. So how to get this value? So apply sigmoid function on this. Call that as sigmoid, like the sigma of a I of k. So what is that equal to? That's equal to 1 divided by 1 plus e minus a I k. Okay, this is your forward pass. Now take these values. Okay, take these values. These values are pretty easy. W1, W2, W3, and this is starting from point 1 to 1.2. And bias 1, bias 2, bias 3 are all similar. And you have to do this for all the layers. You have to compute these two values. I'll give you maybe 2 minutes to compute this. So one more thing before going ahead, we can also write in the vector form. So this was element wise form. So we'll write in vector form. So how can we write this in vector form? So again the same thing. You have to compute ak. So what will be ak equal to? So this will be wk. Take the whole matrix and multiply it with hk minus 1 and then plus bk. Pretty easy. You don't have to do element wise. So you will use this for the computation. And then once you have to compute this, you have to now compute h of k. So that will be sigmoid of ak. And how is sigmoid applied? It's applied element wise. Okay, I hope that you got the point. Use this formulation to come up with the values of these things. So now if you understand the problem setup and you might have been trying, please now focus here, and I'll do the calculations for you people, and you might have to keep an eye on the calculations. I have tendency to do wrong calculations. So what we'll do is we'll do for each layer. So we have to basically compute a1 and then h1, okay, a2 and then h2, a3 and then h3, and these will be all vectors. They'll belong to r2 cross 1. So they'll belong basically here. So when you apply this, so this layer basically will have a1. So this is pre-activation. Okay, and then we'll have h1. So this is hidden layer 1. So output of hidden layer 1. So okay, this will belong to 2 cross 2 because you can play 2 cross 1 because clearly you can see that there are 2 neurons over here. Again here it will be a2 and h2 over here, and there it will be a3 and h3 or hl that we call. Okay, these things we have to compute. Again, we can do it element wise and we can do it vector by vector. How to do it element wise? So we have to compute a1 1, a1 2. So this is the first a1, the a1 that we called, and similarly we have h11, h12. This is related to h1. So we have to compute all these values. Let's start with a11. So let's start with a11 computation. So how can we compute that? So we have to take the whole weighted sum. So if you do that, so you will basically take 0.1, okay, multiplied by 0.1, okay, because we start with 0.1. If you see this matrix, okay, if you see this matrix, we are fixing this, we are fixing one row. So we are fixing this row over here, okay, and then multiplying with 0.1 and 0.1. Okay, so now the calculation over here that is written 0.1 multiplied by 1. Okay, so you have that whole w and you multiply that by x plus 0.2, and then you multiply it with, again you multiply it with 0 because second entry in that is 0, and then plus you have bias. So bias is 0.1. okay, this is your w and this was your first and this was your first element. Okay, so in that, if you see that whole matrix, you take this entry and this entry, and then you multiply it with x. You had the x vector, you multiply with this and this. So basically this is the multiplication. That's what this is, these two things and these two things. Okay, and then this is your bias. You can write the names also. So but here a11 is equal to, so this is equal to 0.2. okay, 0.1 and 0.1, and this goes to 0. This is 0.2. again we can compute a 1 2. Similar, now we'll go to second row of that. If you have this W, you'll basically go to this entry over here, okay, and you'll compute that. Again, similarly, that value is 0.3 multiplied by 1, okay, plus 0.4 multiplied by 0, plus again the bias is same. So this value comes out to be 0.4. Okay, this is the second entry of this. So this is this entry, and you're multiplying it with this, and then this entry multiplied with this, if you can imagine those matrices. And now with this A1 is done, and now we can compute H11, H12. Okay, how to compute this? Just apply the softmax. So after applying softmax on this, you can do that. 0.2 softmax and 0.4 softmax of this. So this roughly comes out to be, so this is equal to 0.54, and this is roughly equal to 0.59. These are the values. Okay, in order to do it in vectors, so how can I write in vectors now? A1 directly is equal to, this is equal to 0.2 and 0.4. So if I have to write H1, so H1 is equal to 0.54 and 0.59, and some other values are here. So I'll just write these things. So we are done with the first layer. Okay. Now can you people do it for layer 2? Take the layer 2 matrices. Again, the same thing. You have to go to previous values because you have to store these values now. That's why I was telling you people, you have to cache these AK and HK values. You have to cache these values. Okay. So if you can do, because once you do the computation, you'll use previous computations of some sort. Okay. Can you do this on your own? So now if you see this, so what we have done is, so I told you to do this calculation. So we're first computing each element of the vector. So we have to compute A1 and H1. So in that A1, we have to compute A11 and A12. And similarly for H1, we have to compute H11 and H12. So A11 is equal to, you have to fix this W, this basically this is W1, this is W2. Okay, and then you can say this is W11, this is W21, something of this, so W12. So what you can do is you can take this whole row and multiply with this. So you will get this value. And what you can get, you will get this whole value. This element into this is this. So this element multiplied by this is this, and then this plus bias. And we got this value. And after applying activation, we got this. And we can do it for the second layer again. So for this, we have to compute A2 and H2. For this, we have to compute A21, A22, H21 and H22. H21 and H22. Again, do the same calculation. Now you will have to take W2. So that bigger matrix. So if you see this W2, this is that. So you have 0.5 to 0.8 and you know the bias. So how can we compute this? So now let me do the calculation. For layer, this is for layer 2. So we have to compute A21. So this is pre-activation of the second layer. So now this is equal to 0.5 multiplied by whatever we got from the previous layer. So we got 0.54 something. Okay, plus, and then 0.6 multiplied by whatever the second element in that, basically HK minus 1. So in this case, it is H1 because we are doing for H2. And now this is multiplied by whatever value we got 0.59 there plus 0.1. So this roughly comes out to be 0.73. Okay, if I don't remove all those points, so this is that value. So A22 is equal to, this is 0.7 multiplied by 0.54 plus 0.8 multiplied by 0.59 plus 0.1, and this roughly comes out to be 0.96. Okay, and then you have to apply activations on this. This is H21 and H22. So these two things come out to be after applying the activation. This is basically activation of 0.73 and this is activation of 0.96. Okay, and you have to apply sigmoid activation. Sigmoid basically is 1 plus 1 e to the power minus of this value. Okay, so these values can be directly written now. So the values that we get over here is 0.67 and this is 0.72. This is all approximate values. Okay, another vector that we got is A2 and H2. So A2 is the pre-activation and this is after activation. So this is 0.73 some values and then 0.96 and some other values, and after activation we got is 0.67 and 0.72. So this is for the second layer. And now similar calculation for layer 3. So what we have to do, take this W3. So W3 will be a matrix of this sort in which we have 4 elements. We don't consider them as 0, so these are 4 elements. Okay, and then we have this value H2. We have to compute H2 that we just computed. We just compute H2. So H2 values are here and here. So in the first go, if I have to compute A3 and we have to compute H3. So A3 contains 2 elements, A31, A32. And similarly for H3, it contains H31 and H32. Okay, so how to compute this A31? So I'll fix this row. Once I fix this row, I'll multiply with this. So I can multiply then afterwards with this H2. This is my H2. Take this element, multiply with this. Take this, multiply with this. So if I do that, so I'll get A3's value. So this is the matrix. If you see that matrix, so that matrix starts from 0.9. So 0.9 multiplied by whatever the value we got here. So that is 0.73, 0.67 rather, 0.67 plus 1.0 multiplied by then the second value that we got in H2. That was 0.96. 0.96 after applied activation we got 0.72, and then we add bias. So this roughly comes out to be 1.4. Okay, so I can write over here A3 and H3. So this is 1.4, and similarly you can compute the second value A32. Do the same calculation, and now you can take this row of W3 matrix and multiply it with H2 and then add the bias at the end. So you will get this to be 1.71. So 1.4 and 1.71. This is A3, and we have to get output and we have to apply activation on this. So once we apply activations on this, this will be 0.80 and 0.84, something of this sort. Okay, now you have applied forward pass and you got all the things that you want. The vectors that we wanted was AK and HK for all the layers. Okay, we got this because these were our, so once we had these parameters, we had these W's and bytes were parameters, and these were our hidden inputs. Basically, these are HK were hidden inputs after activation, and this was our hidden input before activation. Or generally, we call just these as hidden inputs, and these are affine transformations. So once we have this, now the first thing that we have to do is we have to compute loss. So in this case, we'll use simple loss. We'll use mean square error loss. Okay, so that we can compute derivatives easily. So we have this mean square error loss. Now based on this, we made some prediction. Okay, so if you see, this is our prediction, suppose 0.8 and 0.84. Consider this as prediction if we don't apply any output function. So now if you see MSC loss, so how we can compute loss? So loss function over here is equal to 1 divided by 2, and then summation of I goes from 1 to 2, and we'll take these values. We'll take hi of 3, whatever value is there, and then minus yi of 3. Okay, and if this is just yi, and then we'll square it up. Okay, that's what our value is. So you're basically taking that particular value and you're comparing, because we have two output neurons. So if you see our input, so our input was 2 inputs and 2 outputs. That's how we construct the network. So input, if you can clearly see, this was our input and this was our output. So once we give this input and we expected this output. Okay, and now we construct a neuron like this. So this is our input layer based on what input we are giving, and this is our output layer based on what output we are expecting. And now, as we know, we have calculated loss like this. So this loss is element wise loss, if you see. So we are computing for each element. Okay, and then what we can do is we can add them up. We can see how much off they are. So how we can compute that? So we'll compute 1 divided by 2. The first entry that we got 0.80, 0.8. Then we subtract, because the value in that was 0. So we had vector 0, 1. We had to predict this. Okay, so we got this. The actual prediction should have been 0. Okay, and then we have to square it up. Plus, and what we should do is, the second we got is 0.84. And then this should be subtracted from 1. We should have got 1. We got this value. And then we should square it up. Okay, and this 1 by 2 is for both the values. So if you see, this is our loss computed for both of these points in the vector. So if you see this loss, the loss is 0.337491, something of that sort. And when we perform this calculation first, so if I can directly write the loss, so what we basically try to do is we did this. So we did 1 by 2 value of h3, take that whole and subtract it by y, take the norm 2. This is called norm 2. Okay, and that was equal to 0.3374. And I told you loss is a single number. So here you can see this is a single number. This is your loss. Now your goal is to decrease the loss. The goal is that this entry, so you have two entries. You have h31 and h32, and your output basically is y1 and y2. Okay, y1 and y2. These are your entries. And this entry y2 is 0 and this is 1. So you want this entry to be as close as possible to 0, and you want this entry to be as close as possible to 1. And how can you do that? You have to adjust these weights and bias. You have to adjust weights 1, weights 2, weights 3, h1, h2 and h3. You have to adjust those things so that you get these values. And now how to adjust this? You have to apply backpropagation. You have some values and you know all the values in w1, w2 and w3. You know all the values in h1, h2 and h3. And you know how to perform backpropagation. Now we'll perform backpropagation by hand. We'll just do one iteration. Okay, we'll do one iteration of backpropagation, and then we can adjust the values by using the gradient descent. So everybody clear on this point? Just a caution, as I was telling you, we will not just do it for one point in real world. So we'll have a batch of points. Let's suppose we have 64 points. So we'll do this forward pass for all 64 points. And what we can do that, and then we'll get for each point, we'll get one loss. And we'll keep on adding these losses and we'll find average loss. Okay, when you compute a loss in the network, you're not just doing it for one point. You're probably doing it for one batch. Okay, and you're not also doing it for whole points. You might be having 1 million points. That's why you're doing multiple epochs, or you do multiple iterations through the whole data set. And now in order to tune this weights and biases, in order to nudge these values, in order to get the network into the right direction. So we'll use backpropagation. So in the backpropagation, the first thing was if you remember the previous lecture, in that what we did is we first computed what's called an error vector. So we call that as delta k. So this was error vector. Now from here I'll apply backprop. So this is our backprop. So in that, if you remember, we can compute delta k. So what was this delta k? This was error vector. Or if we take this delta k, again is a vector which is computed at each layer. So we have ak, hk. So this was our pre-activation and this was our after activation, and this is an error vector. So how much error? Because this error is propagating. So we defined it so that we can simplify the calculations in backpropagation. So how do we define it? We said delta k basically is defined as dou L, take the loss function and take its derivative with respect to ak. Take its derivative with respect to pre-activation. Okay, this is how the error was defined. Okay, so if I have to take one element, so delta k of I, so this was equal to take this loss function and take the derivative with respect to the ith element of this. Okay, I hope this is clear for everybody. So this was, and in this case, this delta k, if you see, this also will belong to R2. Okay, this error vector also, this will be a gradient, this will be we'll have derivative of vectors, and in that we'll have two derivatives, and we can call this a gradient. And now what we can do is, what is the intuition behind this? So this delta k basically, this is blame for each neuron. So if I take delta k, this is for the blame for each layer. I'm saying that this is the problem that you had. You have to do some adjustment into your weights so that I can get this error less at each layer. So that's why we define it as error. So why? Because this term over here is telling you how better your layer, how better these errors should have been, so that you contribute towards least loss. So that's what this delta k is telling you. This actually we can call it blame factor or error. So delta k blames, now it blames each neuron. So it blames each neuron for its loss because it has loss, and because it got computed because of this. So it got computed because of this AK, and AK got computed because of weights and bias. So it will blame each neuron for its weights and bias. So it will say, I have this loss because of these weights and bias, so I'll have to adjust that. Okay, now how to do that backpropagation? We know that we have to start it from last layer, layer 3. So we'll compute delta 3. So delta 3, now in this delta 3 basically will be equal to delta 3 1 and delta 3 2, something of this. So this will be error at the last layer. So okay, now how to compute this? So if I compute this delta 3 of I, so what will this be equal to? So this will be equal to partial derivative of loss with respect to delta A, and we have to go to this H, and then we have to go with this. So basically we have to compute this A I of whatever the 3 is. But you know that this comes from this value actually comes from H. So we can use chain rule. So what will chain rule say? So DL loss, take the loss function and take this H value. And H here in this case is 3. So H3 of I. Okay. So if you see the neuron over here, you can see this. So this is my last layer. If you understand this part, it will be easy for you people to understand this. So now you had this layer. So I wanted to compute loss with respect to this A3, with respect to the whole of that vector. Now I am taking A31. So in order to compute that error vector, so I actually came from, so this is my loss. How did I compute loss? So the computed loss was computed from this H and then our original Y, and I got this loss. And I have to compute how can I nudge this value A3 so that this loss is less. So it goes to H3 and then towards A3. So that's what I am trying to do. I have to compute delta 3 of I. So in order to compute that, I'll take dou L by dou HI3 and multiplied by, and again I'll use that now in order, because this HI3 we got it from activation function. So I'll just write activation function F dash. So because we have to take derivative of that because of chain rule, and that will be equal to AI of 3. Okay, the activation function was applied on HK because I had to compute this. I'll again write it. So I had to compute dou L by dou AI3. This is what I had to compute. But you know, I have to expand this. So how can I expand this? This dou L by dou H3i, and you have to apply this dou HI3 divided by dou AI3, something of this sort. But you know, this thing we got because of activation. So we applied activation on this. So if I can expand this again. So if I can expand this, so this is equal to this is equal to dou L by dou HI3 multiplied by dou, how did we get this H3? So we got it by AI3. Okay, divided by AI3. Now this is equal to dou L by dou HI3, and this is multiplied by, take the derivative of, because this function is our function that we activated by activation function. So this is value is equal to this. Is it clear for everyone? This should be pretty basic for you now. So now how to compute this? So if you see, you have to compute this H3i, so you have to compute H31. So now because you know that this is an MSC loss, so this loss we have to compute dou L divided by dou, actually I should not write it, I should not read it divided by, so this is dou L by dou H, and this is what I have to compute over here. If you see this one, this one over here. So this is what we have to compute. So this value. So dou L by dou hi3, and this is a value that you can get easily from the sigmoid function. So I have to compute this. So how to compute this? So because I know this is this is mean square error. So for mean square error, if you take derivative, it will be equal to hi3 minus yi. That I have clarified in the previous session. I said just pause and come up with this derivative. If you have to take a loss function with respect to this, and you know you have to take derivative of mean square error function, and you will get to this. Okay, now I will compute del 3, del 3 1 and del 3 2. So I have to compute del 3 1 and del 3 2. I have to basically compute error vector, that blame vector. So it blames on neurons. Okay, so now this is equal to, so what is this equal to? Take this h13 and minus yi. Okay, so and we know that, we know what is the value of this. The value that we have over here is 0.80 minus what is the actual value? The actual value was 0. Okay, and then multiplied by, you have to take derivative, you have again take derivative of the activation function of the value over there was 1.4. If you see that value, the value that we have over here, this ai3, this is 1.4. You have to take again derivative of that and that activation function. So if you compute these things, if you take the derivative of sigmoid function, and if you apply this value on that point, you derivative and compute derivative at this point 1.4, and you multiply with this, so you will get the value. The value is equal to 0.87. So this is roughly equal to 0.807. This is something of this, and now you have to compute again same thing. So this should be h3. This was h31 minus y1. Now you have 2. So you have h32. You know that value is equal to 0.84. I think. I suppose so. Yeah, this is 0.84. I have to see the right calculation, and then I have to subtract it because I am computing the second thing. So I have to compute. This is minus 1. Okay, and then multiplied by f dash of whatever value that was. So that value was 1.71 something. Okay, 1.711. And if you compute this, so this roughly comes out to be minus 0.152, something of this sort. Okay, so this is the value. So if you see, this is that value, 0.1529. Okay, so I am carefully seeing the values. Let me. So we compute this value, and one thing that is missing over here. So we are computing. We have just computed this. Okay, so this is equal to, let's suppose this, and once we have these values, so we have to multiply them with this. So this is 0.807, and then this is multiplied by 1 minus 0.807, and the whole value. So this actually comes out to be 0.12. So this is the value that we want, that we are interested in. Similarly, doing the same thing for this delta 3. So this over here, if you see, this is 0.8, take this 0.84, and then you take 1 minus 0.84 this, so this is equal to 0.019. Okay, so similarly, if I now write delta 3 in vector form, so delta 3 is equal to h3 minus y, and then you have to take this Hadamard product, basically that element wise one thing, and then you have to take f dash of a3. So how to take that? So this delta 3 is equal to, take the whole vector h3, so this is 0.80, and then this is minus 0.15, so whatever the values we got, and then Hadamard product with 0.15 and 0.12. So this comes out to be 0.125, and this is minus 0.01. And calculations can be here and there, but I just am showing you the method. Okay, so what is this saying? So negative, we are getting some positive and negative errors. So they are saying under prediction and over prediction. We have to adjust these values somehow. Okay, now we have to back propagate these errors. Okay, so in order to do that, this is for last layer. So we have to do the same thing for k is equal. This was for k is equal to 3. We have to do the same thing for k is equal to 2 and k is equal to 1. That's what we have to do. So far, what we have done is, so we have computed these things for this layer, for the last layer. Okay, so we are computing for this layer, error for at this point particular. We have to compute this, and then we'll adjust these values accordingly. Now these values will be used, and now we'll cache these values again. We'll cache the values. We'll have to cache this value. We'll have to cache delta 3, a3, and h3. These values have to be cached. Okay, so once we have these, now we'll have to compute delta of 2 for the second layer. Again the same thing. So we'll do it element wise. So you know we have to run the loop. So what was the value of that loop? If you have to compute from k is equal to, so backwards, k is equal to L minus 1 till 1. So if you remember that, so what we try to do is we try to compute delta k. So we can do it element wise, delta k of I. So what was that equal to? So that was equal to f dash of aik, take derivative of this, and then multiplied by summation of L goes from 1 to 2. So in this case, this W L is fixed. So we have this I is fixed, and this will take k plus 1, and then we have this delta of L k plus 1. Okay, this is how do we compute in element wise. So I think previous we explained this formula directly for all the layers. Okay, I explained this thoroughly in that class. If you don't remember that, please go through that. So if you have to compute any error for now the kth layer, so you'll use the error that came after it, the basically error that we computed before, but in the whole network that error comes after that. So this is the layer that we computed. Okay, this is the layer that we're interested in. So this layer will get computed first, and then we can compute this. That's why it's called backpropagation. You are computing backwards. Now for layer 2, and in the vector form, so delta k is equal to w k plus 1 transpose, and this delta k plus 1, and dot f dash of ak. This is what you have to do. This is in vector form and this is in scalar form. So now we have to compute for the layer 2. I'll do for layer 2, and for layer 1 you can easily do. And once we get the values, and you have subtract these values. So for layer 2, let's suppose for layer 2, basically where k is equal to, by layer 2 I mean k is equal to 2. Now what we should do is, so we have to compute these values. You have to compute the value. So how can you compute the value? So you have to compute delta 2 of 1 and delta 2 of 2, something of this sort. So now computing this value, so you will take WL1 and you will take this third matrix, okay, and you will take delta of this delta L of 3. So once you perform these computations, perform sigma of this, so you will get it to be 0.9 multiplied by 0.112 plus 1.1 multiplied by minus 0.01. I'm just writing the calculations here. So this will roughly come out to be 0.104. You are computing the summation part. After that, you have to also compute the derivative, the thing that I wrote here. So once you compute this part, you also have to compute this part, then multiply them together. So once you do that, so delta 1, 2, so plus the other part, so whatever that was, and this comes out to be 0.0199, something of this sort. Okay, again you have to compute this. So once you compute this, so this value is 0.020357. So again, seeing this, so you first have to take this summation and take the W matrix k plus 1 matrix, because you are computing this W of k. Take this matrix and then take the error matrix and sum that up, and then whatever activation it was used, compute the derivative of that and multiply these things together. And this you should be well versed with from previous lecture. And once you do these computations, you will get value. You will get value of this error. You will basically get delta 2. And similarly, you will have to compute delta 1. Okay. So delta 2, if I write values directly, or if I write in vector forms, or for you people, I write in vector form. So this delta vector is equal. So this is W3 transpose. So first we have to do transpose, and then we have to multiply it with this, and then we have to add bias towards. We have to multiply this with that Hadamard. So if you Hadamard multiplication with this vector, so f dash of ak, in this case, f dash of ak. So a2 in this case. So once you compute this, so if you take this W3 matrix and transpose it, and then multiply it, if you compute these two values, so the values that we are getting over here is 0.10 and 0.101. Okay, this is 1.00 and some other values. Okay, and then once you apply this f dash of a2, if you compute this, and you will get the value as 0.19 and 0.20, something of 0.199 and 0.195, some values of this sort. So again telling you, so take this W3 matrix, transpose it, multiply with the vector that you already, error vector you computed, and this is the activation that you applied on this, and you will get some values for this, and you will get some values for this. So once you get these two values, and you will element wise multiply them, okay, and you will get this delta 2. So the value of delta 2 over here is now equal to 0.0199 and 0.0203, some very close though. Okay, is it clear for everybody? Is delta 2 clear for everybody? And now similarly you have to do that. Now you have computed delta 2, you have to now compute delta 1. So what is delta 1 equal to? Again take this, take the whole matrix and then apply that. So in that vector form, this is W2 transpose, you apply transpose on this and multiply this with delta 2, and then apply, you have to perform Hadamard dot product with the activation of A1. So now you have this matrix with you, you have this vector with you, okay, and you have this activation as well with you. Okay, so what we can do is, so on performing the computation, this vector comes out to be 0.006, this is 6002, and this comes out to be 0.006796. Okay, again what is this telling you? So errors are diluted as they propagate backwards. So this is what it's telling you. So now we have to update these parameters. So we have to do this element wise, we can update. And now with this we have all these delta k's. Okay, all these things are gradients basically. So once we have these, so what we can do is, we can do element wise with this weight. So you have delta k's. So now what to do is, so you have this, basically you have to compute this. So actually the computation actually was to be done was this wij of some particular k. You have to compute the loss with respect to some weight. Now you have these delta k, you have all the deltas. You have this delta 1, you have this delta 2, and similarly you have this delta 3 over here. So once you have this delta 1, delta 2 and delta 3, so these are values. So now basically the task was to find how can we nudge these weights and biases so that we'll see how a loss function impacted. So here, so if you have this delta now, so based on this you have to compute this, and you have to compute this bi of k. This is what you have to compute, and you know what is this equal to? Previously we have also seen this. So this over here is equal to delta k of I multiplied by h j k minus 1. Okay, k1, this is what it's equal to as per element wise. Okay, so again similarly for this, if you have bias, so what is this? This is directly equal to delta I of k, and we have again seen this in the previous lecture. How do we arrive at these results? So in order to see backpropagation again, so what do is we computed delta k is basically the error vector, and then we use those error vectors to compute other delta k. So once we had these delta k's, then the need that we had is we have to compute what is the derivative of loss function with respect to the weights and with respect to biases, and then we use that error vector and multiply with this, and we know how did we get over here from the previous discussion. Similarly, if you have to write in vector form, delta k the loss function divided by of this k vector k matrices, and what we can do is we can directly write it this is equal to delta of k h k minus 1 transpose. Okay, and similarly for dou L by dou bk, if you have to take derivative of loss function with respect to the whole vector bk, so you will get this delta k directly. So this belongs to R2 and this belongs to R2 cross 2. We did the dimension check also. If you remember, we did the dimension check. Okay, now we have to compute these values. How to compute? Again, layer 3. We'll start from layer 3. Okay, basically compute these values. So for layer 3, we have to compute these values. What is the derivative? The actual derivative that we want to subtract. Okay, so for layer 3, this should be 2 cross 2. So if you compute this, if you take all of these things, if you take this vector and you multiply it with this vector, you transpose that, you will get this. Okay, so how to do that? You know the value of this, you know the value of this. So on multiplication, what you will get is, so I'll directly write the values. So if I write values, so we have to compute dou L by dou W3. This is what I have to compute. Okay, these values come out to be, so you will basically take this vector. This is a 2 cross 2 vector. This is a 2 cross 2 vector. So we'll get 4 cross 4 vector. So this is 2 cross 2 0.1257 something. So this is minus 0.019, and then you have to multiply it with again. This is 2 cross 1, 1 cross 2 vector. So this is 2 cross 1, this is 1 cross 2, you will get 2 cross 2. So this is 0.657 and this is 0.72. So once you multiply these two things together, you will get 2 cross 2 matrix. So this is 0.084, 0.09, this is minus 0.01, this is minus 0.014, something of this sort. So these are the gradients. So this over here is a single derivative with respect to that particular element, second element, third and fourth, and now you will use these. What will these things give you? So these things basically give you the steepest ascent, and you have to descent. Okay, you will use these values for each. So you will take the original W3. So this will be original W3 now, and you will subtract this. You will say whatever was the original W3 and minus some eta times, some learning rate times this matrix that you computed. This. Okay, this you will use this, and again similarly for this dou L by dou B3. You will similarly do this calculation as per the formula, and you know how did we get to this formula? You have directly used this delta k. Okay, the values for delta k you already know. Again for layer 2, now this is for layer 3. So for layer 2, what do we have to compute? So for layer 2, we have to compute dou L by dou W2, and you can do it element wise as well as vector. Now I am doing it vector notation, but whenever you get time at your home, so what you should do is you should do it element wise first, and then you can take the whole matrix and you can do it in the vector form. So this is equal to, again, you can take dou L. I would have done it element wise, but here I would like to do it directly. So you will take the whole vector first, so that is 0.006, and then this is 0.0067, this is 0.060 multiplied by 10. Okay, and this is for layer 1. Sorry, I'm pasting the value for layer 1 because that's how I got this input x. So I should take the value 0.019, and this value is 0.02. This is 0.54, 0.59. Once you multiply them, you will get a 2 cross 2 matrix of some values over here, and then what you can do is, and then you have to do dou L by dou B of 2, and you will get directly dou 2. And on doing this, then you will have to compute for layer second. Okay, for layer 1. So for layer 1, what you will have is you will have dou L by dou W1, and you will get all these values. So basically, what you are getting these 6 types of values. You are getting this value, this value, this value. Okay, and all of these will belong to our 2 cross 2 matrix. Okay, so these will be your gradients. Okay, and then you'll also get this loss with respect to B1, loss with respect to B2, loss with respect to B3. All of this will belong to our 2 cross 1, R2, because we'll have two values. And now these things will tell you what I told you. So these things, what they can tell you is, they can tell you steepest ascent. So these tell you steepest ascent, but what you are up to, you want to see the descent. So that's why you take negative value of all these values, all these derivatives. So you take negative value of this and subtract it from the original matrix that we had. Okay, so when m is equal to 1, so if you take single point, so when you do this for single point, then in this case I just showed you for single point, the point that we had is x is equal, I think 1 0, and its prediction was y, that was equal to 0 1. So we did it for single point, and then in general we'll do it for batches. We'll take some m batches, m is equal some, let's suppose value 64, so we'll do it for 64 values. So we'll get such 64 matrices for this, 64 matrix, 64, and we'll take average of all of these. So we'll take average for this, average for this, average for this, similarly average for this, this and this. Okay, so we'll basically take 1 by m. So if you write that, so you'll write the summation of curl L by W1. So this will be W1 for first point, W1 for second point, and sum them up for all the m points and take average of these values. Okay, and this W, if I take, this is I value. So how can I write it? So W1, let's consider I over here. So this will be for 1 point, second point, third point. We'll take that matrix and we'll add these things together. So once we add them up, this again will still belong to our 2 cross 2 in this case. So we have matrix with respect to, let's say we take one data point. So we'll compute this dou L by dou W1. Then again for second point, you'll compute this dou L by dou W2 with respect to second point, then third point, fourth point, and all of these. So once you have m points, so you'll take all the sum of these. So you'll have this m W1 matrices now, m derivative, m gradients. So once you sum them up, and then you can take average of all these points, so that you take average gradient, and that is what you will subtract. And after this, you'll use gradient descent. So what I did here, I skipped some calculations, but I suppose that here, if you understood how to perform forward pass, so we'd perform forward pass length, and if you know the formulation for backward pass, that we discussed in detail in the previous lecture, and you should be now able to do it in element wise, in vector form, and then you can write the code for it. Is it clear for everyone? The method of differentiation that you saw over here, this is the method that we generally call symbolic differentiation, because you use the values and you compute the exact derivatives, and then you substitute the values of exact points and you get some values. But we will not generally use it in our autograde engine. So okay, when we will develop our autograde library, let's suppose something like PyTorch, in that we have to perform this backpropagation, but this is very inefficient. So in that, what we can do is we'll use autograd. So in order to perform this autograd, the concept that we have learned will be similar. Okay, but how do we implement this in computers will be different. Okay, as I was giving you the example, if you are learning optimization and you know how to optimize the thing, if you are given a function and you know how to optimize the function, but when you are implementing that in your computers, because you have different hardware, you have different architectures, and based on that, based on all that information that you know about computers, you have to bring this problem into your computational world and to see how can I efficiently use my resources, how can I efficiently use the hardware that I currently have in order to optimize this thing. So that's why you might have heard about computational methods of optimization. You optimize methods are there, but you might be learning separate computational methods of optimizing. Similarly, you saw this backpropagation that we did symbolically, that we did by using symbols. But what we'll do next, we'll use numerical differentiation. Numerical differentiation is basically, you can use direct values of differentiation. F of x, let's suppose plus theta or plus some epsilon, and then minus f of x divided by epsilon, something of this sort. So this we can compute numerically. But again, this numerical differentiation, one is symbolic, the one that we saw over here. This is symbolic differentiation. We use symbols and directly use the mathematical formulations to come with the values and then substitute the values. And numerical value, if you see this, so you can directly use numeric methods. The by definition, this is what derivative means. So this again is inefficient. This is not efficient at all. So what we can use then is, we'll use autograd. So in that autograd, we have two methods. We have what is called as forward method, and we have what's called as backward method. And this backward method is called as backpropagation. Okay, and there the concept of computation graphs will be very important. The computation graphs that we studied probably in some of the lecture. So that will become very important. So just one takeaway lesson in this last 5-minute discussion is that whatever you learn in theory is not necessarily that what you will implement. The concept will remain similar, but the implementation will differ. Why? Depends on the efficient way, depends on the method, and depends how can you efficiently use hardware and the architecture of the computer. So that you should ingrain in your head. So if somebody knows computer science at a theoretical level, doesn't mean he can code it well. So okay, now it becomes an engineering problem. That's what I said. Now this problem is an engineering problem because you know the theory. You know the theory behind backpropagation. Now in order to implement, you have to optimize. You have to bring the efficiency into the picture. Okay, so how to do that? You have to perform this autograde. You have to learn about autograde. You have to learn to somehow efficiently implement this these operations. But results should be similar. It's not that you will give different results. You will give the same results, but somehow you have to use the hardware of the computers very effectively, because computer works on certain hardware, it works on certain instructions, and you have to use that architecture computer in an effective way so that your algorithm performs efficiently. So we brought a problem, we had a problem in real world, neural networks. So we brought that into some algorithmic world. Algorithmic world was we come up with the backpropagation, and now we have to bring that into, we also brought that into the mathematical world. We also wrote some maths, wrote some symbols around that, and then we also have to bring it into the computational world in which we'll perform computation. Okay, that we will probably discuss in the second lecture of this, second series of lectures, in which we'll discuss about ML systems. So in that lecture series, what we will do is we'll first read about autograd, and once we are done with autograd, and then we'll code the autograd. So we'll start a code like this. Okay, I'll just give you a high level overview. So we'll first have to define, let's suppose something we'll perform these operations on. So if you see, we have these neurons. So we'll have to construct this artificial neuron. Okay, in which we have this, each neuron will be associated with weights and biases, and we can perform certain operation on these. We have to perform addition, subtraction, multiplication, exponentiation, or some other values on this, and this also will have some gradients. Now we have this weight W, we have this bias, or they will be having corresponding gradients with respect to that. Okay, and once we apply this, so we'll write, let's suppose something of this sort, we'll write a dot forward, okay, or some network. So we have network, we'll write some network loss dot forward. So it should apply whole forward pass on that network, and then we'll write something, let's suppose a loss L dot backward, or L dot loss first. Okay, so we'll compute loss function, and we'll do then L dot backward. So basically this will compute the backward pass and update the gradients, and then we, based on this, will update this. So you perform the forward pass, okay, then you compute the loss based on that, and then based on the loss you will do the backward pass. Okay, based on the backward pass you will get gradients, which you will use to perform gradient descent. Okay, the next lectures will be specifically focused on this autograd. If you have any questions, I'll take them here.